Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are talking, as you all know, we are doing the electromagnetic radiations. In today's topic, we'll learn about the speed of the electromagnetic radiation, and the main experiment which is involved in that topic is a measurance experiment. So that is the main topic, that how that value of the speed of light in a vacuum, which is 3.00 raised to power 8 meter per second, can be originated. From where you get this value. So that all thought about in this lesson. We'll do with one small diagram which involve that experiment. So Michelson's experiment says that, so how it can be discovered, we can learn about this now. So between 1877 to 1931, Michelson has performed a several experiment to determine the speed of the light. This best measurement in 1926, where they obtained the speed of light of 299,796 plus minus 4 km per second. So they get something like this type of speed of light in that 1926, which has approximately only the 3.5 km per second greater than the currently expected value within the margin of the error Michelin's experimental result. So this is the value they firstly got. After that, they do some main experiment with the lots of equipments they do. Measures shine the light on a orthogonal eight-sided mirror from the Mount Vision in the California. On mountainside Oregonium, 35 kilometers away was the curved mirror which reflected the light back to the orthogonal light mirror. This light has then reflected into the telescope where it would be absorbed. So that all they should do. In form of diagram, they do this thing. What they do, they have this orthogonal which is eight-sided, which is like the type of a mirror, and this is a rotating mirror. They rotate it. And there's an eye and there's a telescope over there, and this is a 35-kilometer long where they have a one curved mirror. So what they do, so from telescope they see that when the light comes to this mirror, they go light from this the mirror and then they reflect it back to this mirror on the another side. This is the one side, they reflect it back, this is the another side. And this is rotating mirror. This rotate continuously. When they go from here and they rotate, they get into this thing, this side of the orthogonal. Why are they doing this? So Michelin's setup was designed so that the rotating mirror had to be in specific orientation for the light to be absorbed in the mountain. This allows for the light to be reflected off the eight-sided mirror and travel to and reflect off the curved mirror at the Mount Sand. So they do the experiment with the rotating mirror to get the speed, that how they reflect it back and how much speed they travel at that time. So firstly they calculate the distance, then they calculate which time they get. So from distance and the time and with the orthogonal eight-sided mirror, they will come to know about the speed. So that's all thing they do, and the observation they get is that. The observation they get is that in the Michelin experiment was during the time light travel from the eight-sided mirror rotating mirror to a curved mirror and back, the rotating mirror would make 1/8 of rotation. When the light is reflected towards this, when the light is touched towards this, like they go and when they go, they rotate, and when they reflect it back to the mirror like light, they only travel 1/8 of rotation. So that's all they observe in the telescope. And when the light returned to the reading mirror, the setup would be in the same orientation it was initially, showing the observer to detect the light. So then they detect the light. So only the 1/8 of rotation can be done in that case, and they calculate the distance, they calculate the time, they calculate the things which is to the velocity. So note, the biggest mistake when we're doing the Michelin type is problems, forgetting to account the light needs to be traveled from the rotating mirror to a stationary mirror in the back. They go two times. They travel the same distance. From here to here, they travel 35 kilometers first. Then they also go back. So 35 into 35. So they have a double distance when we move on to go and back. So you have to know about this. So that's all thing they do. So what they get, so this is the approximate values which the machines get. So use the following data from the mission experiment, determine an approximate value for the speed of light, which is c, and the mirror mission used for the 8 sides. So distance between the rotating and the curved mirror is 35.51 kilometers, and the frequency of the rotating mirror is 527.6 hertz. So from this we have to calculate the what is the speed. So speed c is also the v. Also we can see that c, we also call the c is equal to v. So basically we calculate the v. In that case we calculate the v. And so for v is equal to d upon t. So time we don't know, time we have to calculate from the number of calculations. But a d we also know, we know that d is this 35.51 kilometer, but we have to be in meters because the meter per second we want. So when you divide by this 1000, you get 35510 meters, and it's also like 3.551 into 10 raised to power 4 meters that you can use. And we have the frequency now. So d we know, but we have to find the time. So for the time we'll do some calculation, bunch of calculations. So you know that frequency is equal to 1 upon t, which is the period. So this is the t, and t is also the seconds. So firstly you have to find the what is period. So why we can't find? So this is a process we have to always follow in that type of questions when you get this experiment in the question. So we know the we first find the period. So 1 upon frequency. So t is equal to 1 upon 527.6 hertz. Frequency is given to us. So you calculate the t and you get 0.001895 seconds. So that time is for the one full rotation. When the 1/8 all this orthogonal 8 side, it will go one full rotation. So this is the period of this. So this is for the one full rotation. And now they do the 1/8 of the rotation. So this is the one full rotation. This t is a one full rotation. So this means for time you get 1/8, which is period, which is off rotation. So 1/8 into 0.001895, which is seconds, and when you multiply this out, you will get about 2.369 into 10 raised to power minus 4 seconds. And this is the time for the mirror to make a 1/8 of a rotation. So this time you get, and this time you have to use in the question now. So firstly, for d, we have to calculate the speed of light. For the speed of light, when you have a distance, when this is given to us, so you have to multiply that distance by 2. When you have to find the distance, so you have to, at the end, you have to divide this by 2. So for this, we have the distance, so we have to multiply by 2 because they back and then the same time they come back to that position. So 3.551 into 10 raised to power 4 meters, divide this by the time, 2.369 into 10 raised to power minus 4 seconds. When you calculate this, you get about 2.9976 into 10 raised to power 8 meter per second. So you get in 3 said this, 4 said this. So 2.998 into 10 raised to power 8 meter per second. So it's approximately 3.0. So 2.9 is 3.0 approximately in 10 raised to power 8. But this is the velocity they get, and this has only like 0 point something percent error. So that much accurate answer they missions that when they go that experiment. So this is the most like latest experiment, and we have to know this experiment because this has we calculate the more accurate value from that of the speed of light in the vacuum. So that's the thing you have to do in this, and let's do one more example, which is the full example because you get this type of things in the questions. In that question, in a Michelin's type experiment on 8-sided mirror, it's a minimum of 36,000 RPM, which is the revolutions per minute, or you can say the cycles per minute, same as the period, to see the light. If the major speed of the light is 2.7 to 10 raised to power 8 meter per second, now the v is given to us. So we find the distance between the mirrors. So we have to find the d. So basically, so for d, if v is equal to delta t upon delta t, So what is delta D? V times delta T. So we have to know the V. So this is your V, and you have to know the time now. So for the time, so they've given to us that 36,000 revolutions per minute. So which means you have 36,000 per minute, and you have to convert this into seconds. So 1 minute is equal to the 60 seconds, and minute cancel out. When you divide this out, so you get 600 rps. So this is the revolution per second from the minute. You get the in seconds now, and you also know that the number of cycles per unit time. So this is same like the number of revolutions per second. So this is also equal to the your frequency. So the frequency is now 600 hertz. So if you get the anything in per second, you get to know that the frequency is that. But you have to be in seconds, not in minutes. So 600 hertz is our frequency now. So you know that f is equal to 1 upon t. You have to just find out the period first. So 1 upon 600 hertz, get the t of about 0.00166 seconds. So this is your period now, and also now again the time is 1/8 of the period. So the 1/8 into 0.00166, this is seconds, and when you divide this out, you get about 2.08 into 10 raised to power minus 4 seconds. So this is the time you have to use in now this 2.08 in 10 raised to power minus 4 seconds. So delta D, you get about 5 sets to 50.000113. This you get in meters, but I told you that if you have to find the distance at the end, so at the end you have to just divide it by 2. Because this is from the back and forth, between the meters we want. So this is the total distance back and the again. So at the end you get about, into set this 2.8 into 10 raised to power 4 meters. So this is your delta T you have to find between the meters. So that's how the mission experiment can be used. If they mention that this is a mission type experiment, or they mention that this is the 8-sided mirror you have, so you have to use this formula. You have to do these things. You have to follow these steps. So that's all for this lesson. Now we'll come to know about the more about the EMR. So we already done the 3 lessons of EMR. Now we started with the reflection. We now focus on the light, with how light is reflected, how light can be reflected from the mirrors. So that's all things you have to know. So let me know where do I learn smart, important, and harder. Please like, share, and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till then, stay connected with EduVibe.